Here we have a problem that's very similar to a lot of our block on a slope problems, except we've added a spring. Okay, the spring component isn't that difficult, but I wanted to kind of include it in a more complicated problem and put it all together. So anyways, we got a 10 kilogram mass hanging from a spring that has a spring constant of 1,000 newtons per meter. Okay, the slope is at 50 degrees and the coefficient of friction is 0.2. So as always, on this kind of problem, we want to let me tell you what we're going to do. We're going to try and figure out how far the spring is going to stretch before it comes to rest. Okay, so again, the big thing we're looking at is we're trying to figure out, we're going to try and split it into parallel and perpendicular forces. Okay, parallel to the slope and perpendicular to the slope. So, start with that. We got parallel and perpendicular. So of course we know that when it comes to a stop, the acceleration is going to be 0 in both directions. Okay? Which also tells us that of course the net force equals 0. Now let's go on and list the actual forces and the individual forces that are on this. So we've got the parallel force of gravity, okay, which is going to be mass times gravity times sine of theta. We've got the frictional force, which is going to be the normal force times mu. And we have the spring force, which is going to be negative kx. And as we're looking at that, we know that this force, this is negative kx, but we don't really know, like, why is this one negative? Why are those two positive? Is that really how it's going to be? Well, think about direction. Okay, which way is the spring going to pull? Up. All right? Which way is the frictional force? The frictional force is also going to be pushing up because of things to be sliding down. Okay, and then FG parallel is going to be down. So we actually want to make this one negative as well. Okay, just in order to keep direction constant. And that means that we have 0, well, F net equals 0, which is equal to mg sine theta. Actually, let's go ahead and calculate that out. And we know that this is going to be 10 times 9.8 times sine of 50. And it's going to be 75. We can also calculate this one out, and it's going to be negative 1,000 x. Okay? So we're actually going to stop there. We're going to add these all together in a second. Well, no, I lied. We're going to do it right here. So that's going to be equal to Fg parallel plus frictional force plus spring force. Okay, and we don't know, we know 0, we know this one fully, we know this one, this is our variable x that we're trying to find, and we don't know this one. So we got to figure this out. So let's go look at our perpendicular forces. F net is 0, again we have Fg perpendicular and the normal force. Okay, and that should be it. And because they're the only two forces and the net force is 0, they must be equal. So let's figure out Fg is going to be 10, well, mass times gravity times cosine of theta. And that's going to equal to 10 times 9.8 times cosine of 50, or 63. And as we know that Fn is going to equal Fg perpendicular, we get that is also equal to 63. Alright, so we plug this back in. Here we get negative 63 times mu equals negative 12.6. We can now plug it in down here. We get 75 plus the force of friction, which is negative 12.6, plus force of the spring, which is negative 1,000 x. Okay. That's all equal to 0 still, which should give us 62.4 equals 1,000 x, which means x is 0.0624 meters, or 6.4, sorry, 6.24 centimeters. Okay? So again, we treat the spring force exactly the way we've treated other ones, okay? It's just going to be dependent upon x. There you go.